Hi, I'm Darren and welcome to Level Up EE Lab. Well, I've been kind of busy this summer and haven't made many videos, but I did find time to get the GR-91 out that I bought at Hamvention. I got it cleaned up and I had one major goal to see if I could get it working. Did I succeed? Let's find out. Alright, let's get down to business, starting with some disassembly. And the very first item I'm going to remove is the speaker. It's in a very vulnerable spot here on the side of the case, and I almost poked my fingers through it several times when I made the first episode. There's enough slack in the wiring, so I just cut the connections rather than fumble around with desoldering them. I'll fix up new connections when I reinstall it. Only 2 screws hold it on, so this is a no-brainer move to set it aside where it won't get damaged. Next up is to remove the knobs, and these are really cheap ones. They don't have brass inserts. So you really got to be careful not to torque them down too tight, otherwise you'll just end up splitting the plastic. After that I can remove the nuts holding the controls in place, and then this little panel pops right off. I have no idea if this is the reverse of the assembly instructions, but it really doesn't matter. There's pretty much only one order in which all these parts will come off anyway, including the acrylic dial, which is in really good shape, by the way. Sometimes acrylic splits and cracks over the years. It depends a lot on what chemicals it's been exposed to. That material has poor chemical resistance. Also, if any screws that clamp it were ever over-tightened, that can lead to stress cracks. But luckily I don't see any cracks. I'll have to be careful cleaning it. I don't want to accidentally wash away the paint. Next up is the main front panel, and to get it off I gotta cut the connections to the signal strength meter, then disconnect the dial cord. I'll probably replace the dial cord, it looks like it's pretty stiff. After that there's only a few screws holding the panel to the chassis, and then it comes free. That is after I disconnect the other end of the dial cord. Take a look at the bare chassis. It's pretty dirty, so I'm gonna use the super clean method to get rid of all of this gunk. And I suspect there may be more nicotine residue here than it appears. I've used this method on several other pieces of gear and it works really well. As always, it starts with me taping over the openings in the coils to help keep direct water spray out of them. Next, I move this party outside and I spray the rig down with the 50% diluted super clean mixture. I mostly let the solution and gravity do the heavy lifting, but a bit of scrubbing with a light flux brush does help with the more stubborn areas. I don't let it sit on there for more than about a minute before I rinse it off with regular tap water. I think it's unnecessary to use deionized or distilled water. There's just too much remaining residue on the chassis to need it, and plus I'm not trying to get it that clean. Just want to get all that old dirt and grease and nicotine off of it. And yep, judging by this rinse water, there was indeed more nicotine residue on it than it appeared. Gross! The spa treatment finishes with a couple-hour bake in the sun to dry it out. Now I do flip it over a couple of times so that both sides get evenly toasted. And here's what it looks like after drying. Much better. There's still some gunk on the IF transformer cans, but those are pretty easy to wipe down individually. What I'm gonna tackle next is this bad boy. It's a multi-segment electrolytic cap. This monster has 4 separate caps inside. 3 are used for the DC power supply, and the 4th is in the audio amp. I'll be pulling it off and replacing it with new parts. Now I know some guys will first try to reform the electrolytic in these, but that's not my method. I show no mercy on decades-old electrolytics. They've gotta go. And fortunately, this one was pretty easy to desolder and get out of the board without any damage to the traces. Not quite sure yet if I'm going to fab up a PC board subassembly for the new parts like I did recently for my IM38, or if I'll just solder the new ones directly to the board. Need to give both ideas some more thought. But what I need to do before going any further is to check out the power transformer. If it's shot, then this repair gets a whole lot uglier. I cut the rectifier diode lead to isolate the transformer from the rest of the circuit. I'll just replace that diode later. Then comes the dim bulb tester, and we all know the drill by now.
This item contains hazardous voltage and safety precautions must be followed. If you're following along and working on your own version, you're doing so at your own risk.
And more good news, the transformer seems to be working. Now of course there's no load on it, so what I'm seeing here is open circuit voltage. But doing this test is still better than just measuring the windings with an ohm meter. So what would I have done if the transformer had tested bad? Well, unfortunately, in most cases, that's the kiss of death for most rigs under restoration, especially if it's got a transformer with multiple secondary taps. You're just not likely to find a modern replacement, and good luck finding a new old stock part sitting around somewhere. Folks with more skill than me might be able to find an open winding in a transformer and fix it, or there's always a possibility of finding a parts unit at a Hamfest and just taking the transformer out of it. So that's why I test the transformers very early on in my restoration projects. If the transformer turns out to be bad, the rig's not likely to end up as an episode anyway. The GR-91 has a rather interesting scheme for powering the tube filaments. Looking here at the schematic, notice that even though it has a power transformer, there's not a secondary low voltage winding for filament power. There's only a single high voltage secondary winding that powers everything, including this tap right here ahead of the rectifier diode that feeds into the filament chain. And ahead of the filaments, there's the two front panel bulbs, which themselves are paralleled with a 600 ohm resistor. And then finally, this object called a glow bar resistor. I had to do some research to understand this design, and I think I figured it out. The startup and steady-state filament current is controlled by the glow bar resistor, which is essentially an inrush current limiter. Heathkit seems to be indicating that it has 800 ohms resistance cold and 100 ohms at operating conditions. Apparently, Heathkit was concerned that the cold resistances of the panel bulbs and tube filaments might be so low that they'd be damaged by startup current without an ICL. Now, from what I was able to find online, these glow bars tend to go hooves up, and naturally there's no drop-in modern replacement for them. And sure enough, the one in my GR-91 checks out bad. Assuming that it should be 800 ohms, it's not. It's clearly much higher than that. I'm taking this reading with the tubes pulled, so there's nothing else in circuit with it. So it's gotta go. So what to do about this defective glow bar resistor? Well, I did some online searching, and one common fix is just replace it with a couple of conventional resistors and a bypass switch. Start out high resistance for a few seconds, then after the rig warms up, flip the switch and drop the resistance down. But I'm not crazy about that idea. I think a better idea would be to replace the glow bar with a modern inrush current limiter. So first up, I need to confirm that 100 ohms is a proper value at operating conditions. A quick datasheet check confirms that the lamps and the tubes draw 150 milliamps at operating conditions, so if the glow bar were at 100 ohms, it'd be dropping 15 volts across it. Moving on to the two number 47 indicator lamps, they're spec'd at 6.3 volts apiece, so 2 in series equals a voltage drop of 12.6 volts. I'm ignoring the effect of the parallel 600 ohm resistor because 600 ohms is close to 10 times the effective series resistance of the two lamps, and that's not enough to skew my calculations. So adding up the glow bar, the lamps, and the tubes gets me to a total of 115.4 volts across the entire chain. That passes the sniff test, provided that the power transformer is just a 1-to-1 isolation transformer. Heathkit doesn't show what the transformer secondary voltage is, but they do show the nominal DC voltages downstream, and those are consistent with what you'd get from 115 volts AC on the secondary. But even better supporting evidence can be found in a competitor's radio, the Hallicrafters S120. It uses the exact same tube complement, two lamps with a parallel resistor, and almost the same glow bar. The key difference, though, is there's no transformer. The filament chain is directly powered by AC power. So I'd say it's safe to assume that my calcs are correct. There's 115 volts AC across the filament chain, and thus I can assume I need an ICL solution that has a 100 ohm operating resistance at 150 milliamps current draw. Unfortunately, there doesn't seem to be a single ICL that can handle that much steady-state current and have 100 ohms operating resistance and have 800 ohms cold resistance. However, there's no problem with putting several in series and add additional series resistance as needed. And in fact, others have done exactly that to solve this problem. So here's my solution. I'll use the MF72-200D9. It's rated for 500 milliamps max, so plenty of headroom there. Its cold resistance is 200 ohms. Let's say I put 3 of them in series to get 600 ohms. That's getting pretty close to the 800 ohms I need to limit the inrush current. It only has an operating resistance of 5 ohms, so that's pretty low, and that's also at max current, so at 150 milliamps it will be a little higher. I'll need to add a bias resistor in series with the 3 ICLs to reach 100 ohms total, but first I need to do a quick test to determine the ICL resistance at 150 milliamps. So I'll do a breadboard setup with 3 of them in series, along with an arbitrary 100 ohms of inline resistance, and determine their voltage drop at 150 milliamps. Here's the test. I set my 2718 power supply to about 26 volts. That gave about 150 milliamps going through the series chain, which then results in about 10.7 volts across all 3 ICLs. Notice the metal pan over the breadboard. That's just to simulate the thermal environment inside the chassis. Taking that 10.7 volt drop, dividing by 3 and dividing by 150 milliamps, I then calculate the operating resistance of a single ICL at about 24 ohms. Finally, I can calculate the bias resistor to be 28 ohms, and that's conveniently close to 27 ohms, a standard value. Installation in the rig was a piece of cake. There was room for me to add an additional terminal strip and put the 3 ICLs in series. You can see the 27 ohm resistor hiding behind the leftmost ICL. The purple wire on the right completes the circuit to the rightmost ICL, but I left it unsoldered for now. That's where I'll connect my Keithley later to verify the filament current. Moving on, replacing the bad caps and resistors also was pretty easy. I decided to forego making a custom circuit board to hold the new electrolytics, and instead just attach them to the main board. But that meant I had to put 2 of them on the bottom side. There just wasn't enough room to put them all on top. The replacement caps I chose have 7.5mm lead spacing instead of the more standard 5. That aligned close enough to the existing hole pattern. Oh yeah, I also had to replace the diode I cut out earlier too. And of course, I stood the replacement resistors off the board by about 1/4 of an inch or so to give better air circulation, as they do have some moderate heat to dissipate. Alright, I finished the electrical repairs to the receiver, and I've actually done some of the mechanical reassembly too. I cleaned up the front panel components here, including the dial, and everything cleaned up fairly well. I mean, considering the age of the unit, there is some chipped paint and there's some stains I can't get completely out, but it does look much better than it did. I've also not made the final solder connection for the filament chain. I've actually got it open here and running it through my Keithley here in the background so I can monitor the AC current. I want to verify here that my selection of that 27 ohm resistor and that the inrush current limiters are working correctly. So naturally, I still have it connected up to the dim bulb tester. I have it turned on. Let's power it up here and see what happens. See how that current, we monitor up here, see how the current responds. I'll turn it up fairly quickly here. And it starts out fairly high there, but it's dropping off as the ICLs are heating up. And we can see the bulb is glowing. That's actually a good sign. It means the rest of the circuit is drawing current. It's dropping off a bit here. Let me see if there's any audio. Oh, I hear it making some noise. That's a good sign. So it's kind of leveled off here. I think what I'm going to do is take the bulb out of the circuit and just run full line voltage through it. So I'll turn it down a little bit. Flip this switch, which takes the bulb out, and run it up to 115. The noise got louder. That's a good sign. It means the amplifier at least is working and putting out some noise. Turn it down a little bit here. But I'm really happy. Look at that current there in the background. I'm not sure if it's in focus or not, but it's about 154 milliamps. So that's good. I got 115 volts going into the unit, and I've got about 150 milliamps going through the filament circuit. So that's exactly what I want. So that's a very good sign that I did choose that 27 ohm resistor correctly, and those inrush current limiters are doing their job. Well, as it turns out, a 27 ohm bias resistor is just too low. That's because there's not 115 volts at the start of the chain. It's actually higher, 127 volts when the unit is plugged into mains power. My dim bulb tester can't quite reach full mains voltage, and I missed that in the preceding testing. I caught this issue when I plugged the unit into mains power and checked the filament voltage at V3, and I noticed that it was at 14.2 volts. That's just too high. That'll reduce the filament life for sure. Fortunately, the fix is simple. I just needed to redo my calcs around the higher voltage, and that yielded 105.3 ohms. So a 100 ohm resistor will work just fine. After changing that resistor and connecting to mains power, I verified that I still had 150 milliamps, and now the filament voltages were lower. They were at or below 5% over their nominal ratings. So that's close enough. I moved the camera over to the right-hand side of the radio so I can more easily access the main tuning capacitor. I have not reinstalled the dial cord or the pointer, so I have to do this manually. And of course, be careful where I'm sticking my hand in here. But I want to do a quick check and see if we can actually receive anything. And I've got an antenna hooked up just to the by an alligator clip lead to the antenna terminal on the radio. So let's give a quick listen here on the AM broadcast band. That's encouraging.
Not known at this time. We're working
another station, and look, the meter's working. That's another good sign. And a third station. So good. So that's a nice stroke of good luck there. Apparently, just getting the tube filament circuit reconnected, replacing the electrolytics, and a few bad resistors, I've got this rig working. Now I have to do the alignment, I have to do the rest of the assembly, but certainly very encouraging at this point that I've got it working, and hopefully the alignment and everything else I'm going to do next is going to get this close to factory working order again. Before I could move on to do the alignment, there were several punch list items to take care of. One was to replace this broken clip, which was a quick and easy fix. Next up was to undo this hack job connection to the phone jack. For whatever reason, a prior owner had altered the noise limiter switch wiring and added this extra RCA phono plug. I can't decipher what this mod was supposed to do, but fortunately, it's an easy fix. I happen to have a correct mono-style phone jack in my junk box. And here it is, installed and connected per the original Heathkit design, including connecting the noise limiter switch correctly. There was another mystery mod over here consisting of a trimmer pot and a fixed resistor, which took over the Q multiplier jack. Maybe it was an IF tap? Whatever it was, I took it out and restored the original connection to the Q multiplier jack. The only other internal item that I can see that needs repair is the 300 ohm twin lead connecting the antenna terminals to the band switch. The insulation is literally falling off in chunks. But I don't have any twin lead in my junk box, so I'm just going to leave it alone for now. Last up on the punch list was reinstalling the dial cord. Now I got lucky here. It was in good enough shape to reuse, and it only took about 15 minutes to figure out how to get it installed properly. Not too bad. I've spent hours on other radios wrestling with these stupid things. So I'll take the small victory. Okay, it is time to do the alignment on this receiver, and I'm going to be using vintage test equipment here as much as practical, and I'll walk through the first step I'm going to do here, and it's very common with a lot of receivers. You align the IF section first, and this is a very common IF frequency, 455 kilohertz. So the first step was I got my IG-102 RF signal generator set up and warmed up, and then set it to 455 kilohertz, and I did cheat a little bit on the equipment. I'm using my modern Siglent just as a frequency counter, as you can see here. I got it close enough to 455 kilohertz. But for monitoring the volume control, which is the step here where you're trying to peak when tuning the IF, I am using my IM13 vacuum tube voltmeter. And it's reading about mid-scale right now, but I will adjust the magnitude on the RF signal generator to try to find a peak. And essentially this is a simple process. You connect the output of the signal generator to the input, the antenna input, set the band switch to band number, or band letter B rather, set it to 1.5 megahertz, and then adjust the two coils, the two IF coils, and each coil has two adjustments on it, top and bottom, and you just peak them. You just adjust them until you get a peak output on the vacuum tube voltmeter. I moved the camera over a little bit, and I've got the focus set on the IM13, the vacuum tube voltmeter, because that's the instrument of most interest right now. So I'm going to turn up the output on the RF signal generator a bit, and we'll see some needle deflection on the vacuum tube voltmeter. All right, now I'm going to start adjusting those two transformers and look for a peak. Yeah, okay. I'm not going to show the entire 21-step alignment procedure. For starters, it's about as entertaining as watching paint dry. And also, I kept setting the peaks on the IF transformers too high, and I was driving the circuit into oscillation, so I'd have to dial it down and try again. That alone would have made a complete clown show out of this video. Also, there were many back and forth frequency changes on the signal generator, and that really slowed the whole thing down. So I'll just cut to the chase and say I followed the Heathkit procedure step by step, and I was able to complete all 21 of them without any problems. I almost forgot to talk about the tube shields. The rig needs 2 of them, and I did put them on before alignment. Now, they were missing when I bought the rig, and I did have 1 spare, but the second one I crafted from an empty pop can. I did sand off the inside plastic lining, so it does get a decent connection to the ground tab. Next up is the speaker. Handling these old speakers always makes me nervous. It's so easy for a tool or a finger to slip and poke a hole in these things. And even a stubby flat blade is not that much more controllable. But fortunately, I got it back in place without an oopsie. The final assembly step is reinstalling the cabinet, and that provides the necessary physical protections for the speaker and the top of the chassis. Now let's give it a listen. First up is band A, which is the AM broadcast band. No problems here, this rig's got plenty of punch on this band. I'm skipping over band B, there just isn't activity strong enough today for this rig to pick it up. So let's go to band C and give a listen to some CW on 40 meters. Then some 40-meter sideband.
AmericanContingency.com. I want to thank everybody for participation in our participating in today's net. Hope y'all have a good rest of your day, good rest of your weekend before the work week starts back up. Y'all all take care and get prepared.
And of course, some 10 megahertz WWV action. And finally, some shortwave on band D around 13 megahertz. At this point, I've accomplished what I set out to do here, which was to see if I could get the rig working again. Now, there's plenty more that I could do, not the least of which is repainting the cabinet. It's really beat up. I could also make a new rear cover. That shouldn't be too hard to cut from a piece of masonite. There's not much the front panel really needs. It did clean up pretty well, although it does have some wear and tear. The plastic dial does have quite a few scratches, and the only way to deal with that issue would be to replace it completely, if that's even possible. In addition to the paint and the rear cover, there are a couple of other more serious items in this rig that need attention. The first one is with the 12BE6. The oscillator grid voltage on that tube is supposed to be per the specs that I'm showing on screen right now, but it's actually very low on band C and D. Now that might be compromising the sensitivity on those two bands, so some attention is needed there. The second issue is also voltage. In this case, it's with the 50C5. That's the audio output power tube. Now, it's supposed to have 0 volts on its control grid, or 0 volts DC, I should say, on its control grid when it's running. And it does after it warms up for a minute or so. But during the first minute of warm-up, you can see that voltage pretty quickly ramp up to about 10 volts DC. That concerns me because any kind of positive voltage on the control grid, if I remember my basic tube theory, is a bad idea. That's going to cause the tube to overconduct. Now, because it's transient, maybe it's something that's flaky with the tube and it's normal, but I did check out capacitor C23. That's the capacitor that couples that grid to the output, to the plate of the prior stage. I didn't see any problems with it, but I did replace it anyway, along with C23A and R19 and R20 that I'm showing in the schematic on screen right now. No effect. I still saw that kind of flaky warm-up behavior. So both of those items need a little more troubleshooting to see what to do about it. At any rate, I did achieve my main goal here. I got this old rig working again and saved it, at least for now, from the landfill. What I'll do with it next? Well, it kind of depends on what's next in the queue for Level Up EE Lab. I got some other projects to consider for restoration and some additional work I want to do on my home-built HF transmitter. It also depends on any suggestions or comments I get from you guys. So if you do have something to say, please leave them in the comments below for this GR-91. I thank you as always for watching my channel and sticking with me on this simple receiver restoration. So until next time, bye for now.